Mic check.
Welcome to the session on separation logic. So our first talk is by Remy, and he will tell us how to scale program logics to realistic functional programming languages like OCaml.
Okay, thank you. So I suspect that reading this title, most of you understand what I mean by formal semantics. Most of you understand what I mean by program logics. And if you have one burning question, it's what do I mean by a fragment of OCaml? The short answer is a realistic fragment. We're looking not at a toy model, but we're trying to modelize the real language. And the more detailed answer is, generally for this project, we're looking at OCaml without the object system, and OCaml without the type system. We have an untyped semantics. For this talk specifically, I should say everything else is fair game. That means concurrency. That means all the new features of OCaml 5, all the pattern matching stuff, everything. So for this talk specifically, we'll be covering a sequential fragment of OCaml 5, specifically including the new effect handlers. That'll be one of the main focuses of this talk, because they may be semantically not so obvious to model. So what is Osiris? What do I want? I want to be able to take OCaml files written by engineers, to translate them into an embedding in Rock, and then I want to be able to prove things about this embedding using a strong separation logic like Iris. This is our goal. And immediately, this actually enforces some design constraints onto us, specifically at the level of the semantics. Speaking of the semantics, there is the question, where will we be getting our semantics from, right? OCaml has the reference compiler. It has the language manual. Unfortunately, neither of these are much help. This is an excerpt from the language manual. They're not formal. It's a natural language description. So it'll be down to us to modelize the semantics. So this project has two main parts. The first is we're actually modeling the semantics of OCaml. That's a goal in of itself. And the second is we'll be building some program logics on top of these semantics. So I talked about some design constraints. Specifically, we need to satisfy these three goals. The bottom two are imperative. We need a semantic model that's expressive enough for us to model everything we want to model. Specifically, I'm thinking of effect handlers and concurrency. We need it to work with Iris in order to write our proofs. But then because OCaml is a rich language, we really want a semantic style that scales. That's what I mean by aesthetic, something that's modular, something that composes. We want to be able to define all of the constructs of the language independently and then stick them all together. So we want to be square in the middle here. Maybe to illustrate where some traditional styles would fall on this graph. In my mind, something like small step semantics would fall at the bottom here. They're expressive enough to express all of the things we want. This is a typical Iris style. More recently, we've seen a more denotational approach with things like I-trees. The problem with these is it's not yet understood how to do things like non-local control, like effect handlers and user-defined effects. In effect, our approach is actually going to end up being a hybrid of these two, as you'll see a little bit later. And I hope to convince you by the end of the talk that we'll be reaching these goals. So we've set the stage. Let's delve right into our semantic model, especially this first part, which is we have a layered monadic definitional interpreter for OCaml. Layered because we've got this top level, which is an interpreter, written in a monadic language. That's the bottom layer. We've built up on this monad that we call micro. So this top layer relies on effects provided by the monad. So we're writing our interpreter in monadic style. And in practice, we have this monadic combinator API that makes it so we're agnostic to the implementation of the monad below. We just have these nice combinators we use for the effects we need at the level of the implementation of our interpreter. These effects are things like state, things like non-determinism, things like exceptions, etc. So what we're going to do is going to zoom in to this top level here and have a look at what the interpreter actually looks like. It looks like a structurally defined function in Rock over some OCaml expression E of the surface syntax. If we look at the type here, you'll notice we have a environment-based semantics. And the return type here is parameterized by a type of values and a type of exceptions. Our type of values is purely syntactic, right? If you look, for example, at the closure here, the closure is just a triple with the environment that it captures, the name of its parameter, and the function body. In fact, here's internally the definition for function application. Immediately, you'll notice we have this par highlighted here. This is our first monadic combinator that we're seeing. It essentially means evaluate the two arguments at the same time in parallel. We use this to modelize OCaml's undefined order of evaluation, right? We're over-approximating here. The second thing I want you to notice is because we have an untyped semantics, we have this dynamic type check as clo that makes sure that evaluating the first argument actually returns a closure. Finally, the keen-eyed amongst you might notice that the last call to eval here, when we're actually evaluating the function body, is not permitted by rock. This is because it's not structurally decreasing. This is a non-terminating function. So in practice, we actually have a monadic combinator to give us the effect of potentially diverging recursive calls to eval. We call this please eval. So that's kind of the structure. Now, I mentioned at the beginning that we'll be focusing in on effect handlers during this talk. So let's see what that looks like in OCaml. As of 5.2, I believe, we have this nice syntax for installing effect handlers in OCaml. Performing an effect is just perform, and then installing the handler is adding this effect branch into a pattern match. So this match is saying evaluate the expression E, and then any effect that this generates is going to get caught in the third branch here, giving us access to the continuation K, which we can then resume when trying to handle the effect. At the level of our interpreter, I hope to convince you that this is actually very straightforward. Performing an effect is just calling another combinator, and handling, or rather installing a handler, is, again, just another combinator. I'd like you to pay particular attention to the right-hand side of the combinator, of the handle combinator here, where we're inspecting the outcome of the scrutiny E. We have this O, which stands for computational outcome. We expect in this function to be handling things that are either returned values, thrown exceptions, or performed effects. And then this eval branch's auxiliary function handles the actual pattern matching and tells us in which branch we want to go. Once we've matched on an effect and we're handling it, we potentially want to resume the computation, resume the continuation. In OCaml, the two keywords for that are continue, to continue a computation with a value, and discontinue in case you want to throw an exception at the point where the effect was performed. We use the same combinator for these two, resume. You'll notice here it takes a different type, outcome 2, where we're looking at potentially just returns and exceptions. So the reason I'm showing you this is I think it's pretty transparent. We've got this nice one-to-one correspondence between what we expect the semantics to be, and as long as we trust the combinators to be implemented correctly, this is very clean, very implementable, very maintainable, very scalable. So that's the top level. Of course, there's the bottom underneath. We actually need to implement these combinators. And to do this, we'll have a quick look at this monad. I hope to convince you it's also not too complicated. And we'll do that by desugaring the combinators that we've seen so far. Most combinators follow the same rough shape, which is this stop constructor, some code indicating which effect we're doing, some arguments, and then this ID2 here is just a trivial continuation for the stop. It's just an identity function injecting from outcomes to micro. In practice, this is actually just the Frege monad, right? They use different names in their paper, but we have this parameterized stop, which allows us to do arbitrary effects. And then in our computation trees, ret ends up being a leaf. Now, this is not all we need. We need more. We need more than just the Frege monad. And what I'll introduce next are more structural constructors. So the par and the handle desugar also very nicely into constructors. It's not much more complicated. But you'll notice these things carry micro-computations in their arguments, right? The par has 2 micro-computations that it holds in stasis. The handle has 1 micro-computation as well. So these are why these kind of don't quite fit in the framework of the Fourier monad. And this is almost it, right? We add a few more types of leaves to model exceptions and undefined behavior. And that's actually a whole set of constructors for the monad. Again, this is quite short, quite maintainable, and quite concise, we find. So what's the story so far? We have this interpreter that relies on these effects provided by the monad, but we haven't actually defined how the effects behave yet. So far, they're just pieces of syntax, they're inert. And so I mentioned at the very beginning that we had a hybrid approach to our semantics, right? I said something denotational and stepping. So what we do is we add a stepping relation to this. But we don't add it at the level of the syntax, as you'd usually see in something like some Iris papers. What we do is we do it at the level of the micro-constructors, of these 6 constructors that we've seen. So we have this stepping relation on configurations of a computation and a store. And as an example, if we look at that please eval we saw earlier, we get this rule. If we clean up the continuation stuff here, look at a nice rule where we give it just the trivial continuation, you'll see that the combinator please eval in 1 step steps to the actual eval function. And this kind of open recursion we got is from this paper by McBride. It's well studied in principle. And it works well. Divergent calls are just an infinite chain of small steps. So that's for please eval. For effect handlers, we also have stepping rules, right? So the delimited handler here has this basic rule that says I can step under a handle. And what's more interesting is what happens once the computation under the handle has finished, right? What happens when we want to actually process the outcome of the computation? So 3 rules here, ret and throw are identical. We just pass on the value to the function that handles the pattern matching for us. But something funny happens for the perform here. So the perform itself is as we saw a bit earlier, just a stop code. But you'll see we're allocating something in the heap here. We're taking the continuation from the stop, and we're allocating it at a new location L. In fact, a heap is not only a map from location to values, but also a map from locations to either a continuation or the shot symbol. There's 2 reasons for this. The first is it's actually required in order to get the types to go through. If you don't do this indirection, you end up with a negative occurrence of micro in a type somewhere. So this is the hard constraint. And the second is that OCaml has one-shot continuations. Continuations can only be resumed once. And we need some way to keep track of which continuations have been resumed and which haven't. And we can see that with the rule for resuming. Here, the rule for resuming is if I want to resume some continuation that's been stored at a location L, then I read into the store, find the actual continuation that was stored there, actually compute it, apply the outcome I'm trying to resume, and I update the store to mark it as used. And kind of dually, if I try and resume a continuation that's already been used, then I just crash, undefined behavior. So again, I hope to convince you that there wasn't much complexity in the rules we've seen so far. Non-local control is not necessarily an easy thing to model, but this was very succinct and very close to what's actually in our ROC development. And that's kind of it for the semantics. We've got this nice hybrid approach. And on top of this, we will be building our program logics. So you'll see I have another pyramid here, and there's a reason for that. It's because the architecture of the program logics actually follows the architecture of the semantics. When we build our program logics, we first build a bottom layer at the level of the micromonad. And then on top of that, we end up building a layer of program logics at the level of the surface syntax. Now, the cool thing is we don't have this API anymore. We're just using the reasoning rules of the monadic syntax in the proofs of the reasoning rules at the surface syntax. But once you've done that, you can stay in that top level, which means users never actually have to go back down into the bottom layer. They can stay at this nice level where they're just reasoning about pieces of OCaml syntax. They're reasoning about expressions. They don't have to know the implementation details of the monad. Now, you'll notice it's logics with an S here. And you'll also notice this pyramid is shaded. And that's because we have 2. We have one pure program logic for pure programs. These are roughly programs that can step without having access to the store. And for that, we have a weakest precondition style judgment that says that says M, the computation terminates, and if it is a value, then it satisfies phi, and if it is an exception, then it satisfies zeta. And so the kind of rules you would expect is, okay, at the bottom level, we're reasoning about things like please eval, and then at the top level, we're reasoning about things like evaluations of expressions and pattern matching. And this is kind of a discovery that we made along the way, is that when you want to actually verify programs in this style, you end up having kind of a whole bunch of rules for each auxiliary function in the definitional interpreter, like eval and eval branches. And these end up being kind of their own judgments, which was kind of an interesting thing. And so you end up having one judgment per kind of syntactic construct in the language. And this works well. In the case of pure, it's very automatable, right? These things don't have side effects, so often you can kind of reason on them almost automatically. On the flip side, we have an iris-style weakest precondition that we call impure. You'll notice there's an extra parameter here. In fact, this impure is exactly the effectful weakest precondition from this previous work for reasoning about effect handlers. So I won't go into detail about how this is implemented or what the reasoning rules are. All you need to know is it's the same, lifted from that paper to our new environment. So now we're in iris, so our post conditions are in iprop instead of prop. But the constructions are very much the same, right? We still have this bottom level where we're reasoning about things like handling effects, right? Micromonad. And then at the top level, we're back to reasoning about things at the surface syntax. So things like eval A to E. This deep handler judgment is also from the separation logic for effect handlers paper. And we actually end up with the same reasoning rules as that paper as well, which was quite nice to see. Finally, the two program logics do form a whole. They can interact. We have this nice rule that says, if I can prove purely that some computation has some postconditions, then I can use that fact in impure proofs. So at any point in an impure proof, you can kind of step down into the pure world and maybe use some automation there to complete some easy branches of your program. Finally, just to wrap things up, we have a validation step for our semantics. We have this interpreter defined in rock, and we have this stepping relation. We can actually execute this by using rock's certified extraction to OCaml. Right? The interpreter can be directly extracted into an OCaml function, and then we can simply use the stepping relation by iteratively applying it. And what this allows us to do is we can then test for inclusion of the behaviors that are actually displayed by the OCaml compiler against the behaviors that are allowed by our semantics. And this is all parameterized in order of evaluation, so we can try and mimic the order of evaluation of the compiler if we want to restrain our subset of tests, or we can just model our non-deterministic order of evaluation if we want. So to conclude, this is the kind of the full picture. What we have so far is a very, very large subset of sequential OCaml, including effect handlers. Current work in progress is happening on concurrency. That's the next step. And then finally, I mentioned at the very beginning that so far we have an untyped semantics, which is fine, except when you want to start thinking about modules, because suddenly you need to know about the module signatures and which fields to import and which ones not. So we need some reification of the types, which I think we'll get to as soon as we finish concurrency. Thank you. There are two microphones. Tell me the question, I'll repeat it.
The question is, first, thank you for the talk. The question is, so you showed nicely your two logics. I'm curious if, I was wondering if this okay? So thank you for the talk. You showed your two logics nicely. I was curious, does the pure logic actually exist in the sense of, is there a real definition of it? Or could you just have it as derived rules for the impure logic? I mean, you showed this embedding. It seems to me that it means that every pure logical proof that you have, it becomes an impure logical proof. Why is it, like, is it real, and if so, why?
It does exist, so it's its own weakest precondition. There's its own stepping relation that we relate to the impure stepping relation. That's how we get that rule that the two commute, in a sense. As to why we did it that way instead of just kind of hiding it within the impure reasoning rule is that these kind of abstraction barriers are very hard to maintain in proof assistance. It's very easy to slip, and suddenly you're exposing impure goals in what you thought were pure goals. So it would definitely be an approach. I'm not sure how well confined that would keep it within the proof system.
Okay, so then as a short follow-up, would you say that it's really more of a question of engineering? I mean, with a little bit more, with more experience in being able to sort of wrangle the theorem prover, I guess you would go down back to one logic.
Yes, I think so.
Yeah. All right, thank you.
I mean, there's also the fact that it is a total logic as compared to the Iris one, which is partial. So if you're interested in proving termination of your programs, then you need to go into the pure thing. But you could also say, I can have a total logic in Iris, so that's a debatable point. Yes?
So hi, I'm Cesar. I'm from MPISP. I have two questions. So I think the first is related to the previous question. So you need impure to talk about system calls, or why do you need this impure?
So only the system calls that depend on state. So as we saw, please eval is a system call that independently of state will reduce to eval. So that's pure. And something like handling an effect depends on state because you need to read the state. So that would be an impure.
Okay. And then my second question is, did you try to verify an OCaml program using this, and how easy it is to use your work?
Right. So we don't have a big case study. We do re-implement the case studies of the effect handlers paper. And we do have some small examples that we were working on specifically for the pure sublogic. It's not any easier or harder than any other Hoare logic, is my impression. We end up with syntax-directed rules that you just apply as lemmas. And then you can add a thin layer of automation over that. But it's still deductive verification. Thank you.
Hi, Simon Spice from Jane Street. Have you thought about how extensible the system is? Like, say, if you were to add a bunch more features to a language like OCaml, how would that change this semantics?
So we've thought about the ability to extend it in the sense that we've thought about all the existing features of OCaml that we might want to model, and we've tried to make sure that we'll be able to do those. In terms of extensions, there are essentially two kinds, right? There's adding more effects to kind of just the freer monad. Things like adding more stop codes, that's fairly straightforward and easy. And then there's, if you wanted to add more difficult things, if you wanted to start reasoning about locality, for example, you'd have to re-engineer a lot of things, and that's really not as clear.
Okay. Thanks. Oh, very nice talk. I think I forgot to say that.
Thank you. Let's thank Remy again.